Go ahead and get started now. You can keep talking amongst yourselves and everything. Don't feel like you have to pay attention the entire time.
I will be asking questions though,
okay.
So I want you on edge.
Dr. Karalidi will be asking questions. And we'll also have trivia later, and you can win really cool prizes if you get all the questions right. And some of the questions are mean, and I make them up. But some of the questions are nice, and if you pay attention, you'll know the answer. So that's fun. Okay. So hi everyone, my name is Cashapp, and I'm a third-year PhD student at the University of Central Florida in the Planetary Sciences group. Welcome to our second Astronomy on Tap. We're really excited to have you here. If you don't know, Astronomy on Tap is actually this international network of local public science talks happening in bars, like literally all over the world. So if you don't live in Orlando, you can probably find one closer to you, but you're probably all from Orlando if you're here. So, okay. So tonight we were supposed to have two speakers if you saw our flyer, but one of our speakers is mad down with the sickness. So we have one speaker tonight, but that means that we're gonna have this really cool, like, fun discussion panel thing where everyone can like ask questions and talk about cool science stuff. And of course, we really welcome audience participation. You can yell, scream, say whatever you want as long as it's not like profane or like flat earthy kind of stuff. Let me see what else. Okay, yeah, we have trivia, we have prizes. One of the prizes is like a $20 gift card to here. If that is some incentive for you. We'll have an intermission between our first talk and trivia, just so everyone can kind of like get more food and drinks if you feel like it, but also you can get up literally whenever you want. And in addition to all of that, we have some like stickers and patches and a few other things up here, if you're interested. We have like NASA stickers and stuff. And finally, we are like a public education organization run entirely by grad students at UCF. So any sort of donation that you guys want to give us is greatly appreciated. We have our Cashapp tag up here. It's AoT Orlando. We also have a donation jar if you have cash, but you probably don't. Following tonight's event, we'd really like it if you could fill out our survey. For feedback, there's like a little QR code at the end of your table if you're interested. And also, the Geminids are happening right now, so if you want to see a cool meteor shower, you probably can't see it right now because the sky's messed up a little, but eventually. Okay, and with that, I'm going to introduce our speaker for this evening. So our speaker tonight is Dr. Theodora Karalidi. She is an assistant professor in the Planetary Sciences group at UCF, where she researches exoplanet and brown dwarf atmospheres and works on mapping these atmospheres with observational light curves. And tonight, she will be presenting her talk, Cloudy with a Chance of Sapphires. So, everyone say woo!
Let's see if this works. Excellent. Okay, thank you very much for the introduction. Can everybody hear me? Also back there? Better? Okay, better? It's so weird. Okay, so today I will be talking to you about exoplanets. And because Ken is not here to talk, I added some extra slides, so it will take a wee bit longer than the 30 minutes. So how many of you have heard of exoplanets before? Excellent. Okay, I'm preaching to the church here, right? But planets are planets that orbit around stars that are not our sun. And until 1995, exoplanets were something that was really living in the imagination of people at Hollywood. Star Trek movies, Star Wars, things like this, because nobody really thought that there were any planets outside our own solar system. Until 1995, 1994-ish, when Mayer and Colos, well, they were trying to find something else, they observed one of the stars out there that was having something around it, and because of that something, its colors, as you see here on the bottom, were wobbling a bit back and forth because of the interaction of whatever it was around the star, right, pulling it. And when they put the math down, they freaked out. because it was not making sense. For the first time, that something else was not a star, but it was something that had the mass of a planet, about Jupiter. And not only that, but it was something like Jupiter that was actually really close by its parent star, way closer in than what Mercury is to our sun. So initially they really didn't believe their data, and they thought there was something wrong with their observations. So they waited a whole year and went back and repeated this experiment, and they saw that actually they had observed really the first exoplanet out there. And that is 51 Pegasi b, the first exoplanet we know to date, and that resulted in a Nobel Prize 3 years ago. Now, ever since, in 27 years, this field has boomed. We have more than 5,200 exoplanets that are confirmed. And when I say confirmed, it's because we have about 6,000 to 7,000 more that we think are there, but we need to go back and observe them again so that we know for sure that there are planets and not something else in our field of view. And unless you have been living under a rock for the last 20 years, you have seen in the news a lot of things about exoplanets, right? Now, the vast majority of all of these news you see out there are actually only about that little corner of planets in this plot. That's transiting planets, and everything else is what I'm going to be talking to you about today. Now, how many of you have seen a solar eclipse? Okay, so a lunar eclipse? Better. Okay, so with the transits, what we're doing to detect a planet is we keep on staring at the sun, a star, like our sun, and we wait for a planet to pass by, and when we miss some light, we know there's something there, right? Like what you will see here on the left side. And you will see on the left side, I hope it's visible from all the way back there, that about now the planet crosses and we're losing some light, and the big planet causes a bigger loss of light than the smaller planet, so we know there's something there. We can see how big it is, and also by keep on looking, we can see it coming again and again and again, and we can figure out how far away it's from its parent star. And if we keep on looking at different colors, we can also start seeing the effect of the atmosphere of this planet. And I will come back to these later on. Now, as I said, I'm actually interested in everything else in that graph, and in particular image planets. I like to see them in my pictures. And a really nice example is these guys you see here, these 4 dots that you see orbiting that star are actually planets. It just happens that the system is face on, so we can really see another system rotating, which I find really fascinating. And if we take all the exoplanets out there and we remove everything that's not imaged, this is what we get. And this plot is the masses of the planets in Jupiter masses and the distance to the star in Earth-Sun distances. So for reference, you see Jupiter and Neptune are down there. Jupiter mass, unity, right? And Neptune a bit smaller. They're pretty close in, but you see all of these other planets that we are interested in. They can be really massive, like 50, 60, 70 times the mass of Jupiter, and they can be really far away. Some of these guys, like the ones you see down there, they can be 150 times, 200, even 500 times the distance of the Earth to the Sun. And this is exoplanets, but I'm also going to talk about brown dwarfs. And how many people have heard about brown dwarfs before? Yeah, okay. So brown dwarfs are the other side of the coin to imaged exoplanets. Some people will claim they're stars, but they really aren't. They are planets. They have sizes that are about the size of Jupiter, and they're just really much more massive than Jupiter. And that can be from about 10 times more massive all the way to 80 times more massive than Jupiter. And by that, to bring it a bit in context, it's a bit like you're comparing a Mini Cooper with a semi-truck, right? And not only that, but you get the semi-truck and you squeeze it in the shape of the Mini Cooper. That's what you're doing with brown dwarfs. And this also means that the gravity in brown dwarfs is completely different from what we're used to here, right? It can be from about 3 times what we feel from the Earth, all the way to 330 times what we feel from the Earth. So it's really big. Now, brown dwarfs are coming in all sorts of flavors out there. Some of them are living alone in space, like that little guy you see there. The star is just happening to be in the same field of view. Some have a sibling, like Lumen 16, which is the nearest brown dwarf pair to our solar system. And you can see it dancing around itself down there in the corner, but also around to the galaxy, because they're so close that in just 3 years we can see them moving around the galaxy as well. And some of them have a parent star. And what is a brown dwarf? What is an exoplanet? It's pretty open, right? That's why I say they're 2 sides of the same coin always. Now, as far as temperature are concerned, the Earth, if we didn't have an atmosphere, would be cold at about -6 degrees Fahrenheit. Does anybody know where Jupiter would be in this scale? Would it be hot or would it be cold than Earth? Colder or hotter than Earth? How many say hotter? How many say colder?
You say Jupiter?
Yes.
At what depth?
Huh?
At what depth?
At the top of the atmosphere. So it would actually be colder, right? Because Jupiter is further away from the sun. The sun is the little fireplace in the middle. So Jupiter is further away from the fireplace. It's freezing way more at about -250 Fahrenheit. Neptune even further away at 360, 370 Fahrenheit, -360, 370 Fahrenheit. And brown dwarfs, on the other hand, are living all the way up there, some of them, at over 3,000 Fahrenheit, some really, really hot. And this, if you have been paying attention, might be a bit counterintuitive. I told you that Jupiter is far away from its parent star, so it's really cold. And I'm telling you that brown dwarfs that maybe don't have a parent star, or if they have, they're really far away from it, are really hot. So what's happening? The answer is in the brown dwarfs themselves. Remember, we get the mass of a semi-truck and we have squeezed it down to the Mini Cooper. While doing so, there's a lot of energy trapped in that body. And that energy gets slowly radiated to space. So they start at 3,000 Fahrenheit when they're young, and slowly they cool down with time until they reach temperatures of planets of our solar system and die out in eternity. Now, the other thing that all of these temperature differences mean for brown dwarfs and immense exoplanets is that they affect their colors. Now, how many of you have done astro imaging, like looking up at the sky? Just start with that. How many have looked up at the sky? Yeah, you don't count. So, if you look at the sky, you're noticing that stars have many different colors, right? Some of them are a bit more bluey, some of them are a bit more yellow or red, like what you see here in the Sagittarius image from Hubble. And the reason why is because there are different temperatures. And it might be a bit counterintuitive for everyday life, but when a star is really hot, it's more blue, like Sirius you see down there on the left side. If it's a bit colder, like the sun, which is just like 10,000 Fahrenheit, if I do the conversion correctly, it's a bit yellowish, greenish, like. And something like Proxima Centauri, which is at 6,000 Fahrenheit, is more red. Now, if you follow the story from about 20,000 Fahrenheit to 10,000 Fahrenheit to 6,000 Fahrenheit, you see we go from blue to greenish, yellowish to red. So 3,000 Fahrenheit or colder for brown dwarfs, we're outside the spectrum that our eyes can see, and we're in what we call the infrared. And this is where all these brown dwarfs and immense exoplanets emit mostly. So if you would try to look at them with your eyes, you would never be able to see them. because they are emitting in the infrared. And kind of a funny story, the name brown dwarfs was actually a miscalculation by some people because they thought that if we would observe them in the visible, they would be brown, but they're actually purple. So they're more purple dwarfs. Now, we're going to talk about weather. We have learned what brown dwarfs are, what image planets are, and the next thing that we're interested in weather are clouds. And clouds are everywhere on Earth, right? This is an image from ISS, typical day, mostly cloudy. You can see outside today, same thing. And what kind of clouds do we have at Earth? What kind of clouds can we have? Yes. Yes, we can have water. Is there something else we can have? No, from water, something else.
It's smog.
Smog.
Smog, yeah. Pollution.
No, from water. There's something else we can have. Yes, there's something else we can have from water. Okay, so all of you have seen at some point or another a diagram like this in science school, minus the cool David Bowie Queen at the bottom, right? And depending on the temperature and the pressure in your atmosphere, you can have all sorts of different things happening to materials out there. So our atmosphere has about 28% by volume water vapor in it. At some point conditions are right, we start making water clouds, liquid water clouds. But it can also happen that you start forming clouds high up where it's really cold, and then you get ice clouds, like the ones you see there on the left. These are cirrus clouds, they're ice crystals that directly form a cloud in the atmosphere. And if you're lucky sometimes, these clouds can also cause these really cool halos and sundogs. How many of you have seen sundogs? Excellent. So these are all caused by ice clouds in the atmosphere. You just have ice crystals being formed and you get them and they look amazing. Or you can even have like cumulonimbus clouds like the ones you see there on the left, where you mix water with ice and everything churns, and it's pretty cool. So Earth has clouds. What do you guys think of Jupiter? Does Jupiter have clouds? How many say it has clouds? How many say Jupiter doesn't have clouds? Okay, so Jupiter is a whole big ball of clouds. And because of the different pressures and temperatures in Jupiter, remember it's much cold, you can have water clouds, ice water clouds, but they're really deep in the atmosphere. Much deeper than anything we have in our own solar system. And high up in the atmosphere, you actually get ammonia ice clouds because it's just so much colder. And Neptune takes things a step further, and we can even have ice methane clouds. Now, brown dwarfs, remember they're mostly on the other side of the spectrum, so that is where temperatures and pressures get so wacky that we can get liquid iron clouds, we can get sapphire clouds, we can get silicates and chrome, and all of these things that typically are in solid phase, like your table kind of on Earth, they are actually clouds in these planets, which is what makes them really fascinating. Okay, but how do we know that they really have clouds? We assume kind of understanding their temperatures and pressures, and the answer is in the light that we get from these guys. Because everything around you, from the table to grass outside to the sky, everything interacts with light in a very unique way. And it's as unique as a fingerprint is to a human person. To a human, yeah. What else? To a human. So, by looking at the light and looking at the light from different faces of the same object, we can start figuring out what it's made of. Are there oceans there, for example? Is there life? Is there grass? Or are there liquid iron clouds and sapphire clouds? And here you see an example of this happening where, why is it not moving? Okay, you don't see an example of this happening, but this is a spectrum of, so this is Hubble looking at the brown dwarf, and if it was working, you would see the whole bottom image shifting with time. We are observing the target, it rotates around itself, and you would see the whole thing moving up and down because we see different things coming in and out of view. Now, if you remember that this is an object that is emitting energy to the universe, and you have clouds. At some point you have clouds blocking your view, and then you get less energy from it. At some point it just goes through a clearing, and then you get more light. And this is what you would be seeing down there. And by using computer codes, we can actually use this information and make maps of these atmospheres. And we can start seeing, for example, that there's actually cloud patches, there's dark patches, there's bright patches, and they rotate in and out of view. And not only that, but if we keep on staring at an object, like you see up there in the left corner, you see that the light, the changes of light change with time, which is weather, right? We actually see real-time weather in a brown dwarf like the one you see up there. And Hubble and Spitzer are great little telescopes. Spitzer died, unfortunately, but while they're doing an excellent job for brown dwarfs, they have a bit of a harder time for brown dwarfs when they have a parent star or they're really cold, like the other three images you see here. But with James Webb, all of this will be completely changed, and we're gonna get weather like you see in the upper left corner. Okay, so how do we study the weather other than making these two-dimensional maps, right? Okay, we know there's spots, so what? Weather is clouds. Clouds are 3D, atmospheres are 3D, right? So how do we make that connection? Now, the answer to this is in understanding how atmospheres work. And we are all living in Florida. I hope you all wear your sunscreen all the time, right? It's good. But the biggest sunscreen out there is our own atmosphere. Our atmosphere interacts with light that comes from the sun, and it interacts in different ways depending on the light we're getting. Now, visible light reaches the surface, right? We see things in the day, we see the sun, everything. But does somebody know some of the light that is blocked by the atmosphere? Can somebody name one of the light colors that are blocked from the atmosphere? Like, why do we wear sunscreen?
Gamma rays.
Yes, so UV radiation, right? X-rays, gamma rays, all of these things that would kill us if they were making it through. They would cause so many mutations that we would die. There would be no life out in this planet. All of these are blocked by our atmosphere. So it's really the biggest sunscreen out there. And you see we get all the colors coming down. Some are blocked high up, like UV and X-rays and stuff, but some make it all the way down. Now the same thing works the other way up. So if you have light coming from deep inside, like from a brown dwarf, which is hot, some light is blocked and doesn't make it after a specific part in the atmosphere. Some is only visible if it originates higher up in the atmosphere or at a different, even higher up level, which means that if you keep on looking at many different colors, some of your colors will be affected by one cloud layer, some by two cloud layers, some by three or even no cloud layers at all. And all of these should be leaving a trace in the changes of color you're getting from observing a brown dwarf or an image planet. And that's what we're seeing. You can ignore all the letters here, but just focus at the bright curves and you will see that all of them change differently for the different colors. And this is because they all are coming from a different layer in an atmosphere, and there's different clouds that affect them. So we can use this information to start building 3D maps. And to bring this into something that everybody kind of understands a bit better, this is Jupiter. You all know Jupiter, right? you should have been able to see tonight. Unfortunately, the weather is not cooperating. But this is Jupiter if we have all the colors of the visible. Everything we can see with our eyes. If we use Hubble and we only observe Jupiter in blue, this is what we see from Jupiter. So what happens here? What do we miss in Jupiter? Anybody? What is missing big time? Yes. Yes. So you see here we have on the left we have really obvious dark belts and bands, right? And on the right side there is a red spot. There is the poles, but everything else is like smudged out. If we watch on the right, on the other hand, the bands are back, but suddenly the great red spot is great white, right? So different colors reflect differently with the atmosphere. So we see higher up in the atmosphere, we see deeper in the atmosphere. We completely change the view of what we're seeing. Now, if we play this game of making Jupiter an exoplanet and we smash it down to a single pixel, and we do the same thing we get for brown dwarfs, you see here, or planets, we get here the likers, you see at the bottom right, and you see that they look like what we saw for some brown dwarfs, right? They have their ups, they have their downs because it rotates around itself. And you can also see that there is differences in how the blue color at the bottom changes and how the red color at the top changes. And that is because we had a completely different picture from blue to red of what Jupiter really is. And if I'm using this information to make a map, this is a map of Jupiter, believe it or not. Now, if I make a map, I have this thing here, and you see in the bottom I have like two things there, and the top I have one feature, and I want to understand the weather. I want to understand, like, okay, these are clouds, but are they connected? So there's this intriguing feature here on the right side that it kind of lays on top of one another and they could be connected. What do you guys think? Could they be connected? And what are they if they are? Can somebody guess what this feature would be? So there's a big feature that rotates around Jupiter, and it leaves its mark, and I can see both in the blue and in the red. Somebody? Yes! Yeah, so this is the great red spot. So you can see it in both images, and you can indeed see it in both pressures. And because it's Jupiter, and I can see it with Hubble in all its amazing detail, I know that these features are actually connected to one another, right? But brown dwarfs or exoplanets, we have a single pixel. And that single pixel is all we know about that atmosphere. We don't have this majestic resolved image, right? So there are cases like that guy there. It's an artistic depiction of Tumas 2228. And it has these very intriguing features on its maps that are, one is really high up in the atmosphere, one really deep in the atmosphere. And they are always 180 degrees apart. And we go back and look at it, and it's again 180 degrees apart. So we're all baffled because we don't understand what's happening. Is it like a weird great red spot that's sheared across the atmosphere? Is it two different features that are separate from one another? And there's no way of telling until now. Because last Christmas, all of astronomers around you were super excited. They woke up at 6 in the morning probably, and we all watched James Webb launching, right? It's the best. Now, James Webb is the future, and the future is finally here. And you can see in this nice image from NASA how it has really changed our view of the cosmos. And 2.5 decades, 3 decades, we went from seeing the infrared universe as blobs, like you see them on the left with Y's, to Spitzer doing an amazing job for exoplanets and brown dwarfs, but still, it's not super sharp, and then boom, James Webb, right? And it's not only its size that is amazing for astronomers, but also it has the benefit that unlike Hubble, I love Hubble, don't take me wrong, but a good part of its orbit is behind the Earth for a lot of the object. So you have gaps in your data, which is not very handy. And also, Hubble is limited in the infrared, so it sees a lot of the visible part you see there, but it just enters the infrared, which means we see a really thin part of the pressures of an atmosphere. While with James Webb, we get all of that extra swath there on the right, which means that instead of getting this layer deep down in here, and in the past with Spitzer high up, now for the first time, we're gonna be able to get the whole atmosphere in just one go. And that's why all astronomers that work with exoplanets or brown dwarfs are writing proposals like crazy right now, because the new goal is out there and we all want its amazing data. So I'm gonna leave you with a video of what the weather looks like on brown dwarfs, at least with Spitzer. And this will soon be updated, hopefully with James Webb, and we're gonna learn a lot more. And then I'm gonna take questions. So, questions? Yes.
Do you know if the Roman telescope will be moving on?
Do you know if the Roman telescope will be improving on these observations at all? Or if that's an observation plan?
The Roman telescope will be helpful for AMA's exoplanets. We are trying to squeeze in a polarimeter in there as well, which will help a bit extra. But hopefully it will be launched in, 6-7 years. I mean, in the meantime, James Webb will give us such amazing data. Already the first observations we have from it are way better than anybody hoped they would be. So.
Great talk, Theodora. So these features, they're 180 degrees separated from each other, what you're showing. So it seems like that would maybe be some sort of magnetic phenomenon. Does anybody know what the poles
No,
look like?
so we have been repeatedly trying to study the magnetic fields of these objects, and they are pretty weak, so we cannot really detect them. There have been efforts to find connections of radio variability with light color variability, and there is none. So they're expected to all have weak magnetic fields, kind of like Neptune-ish like. So Neptune is the closest thing we have to brown dwarf in our solar system. So that's why it's really interesting. Honestly, I'm putting a proposal to observe that guy with James Webb because it's so interesting.
Exciting.
I also have a question.
Yes.
So I think up until really recently, whenever, I don't know, I was an undergrad, so 2016, I always heard that brown dwarfs were just stars. When did everyone decide that the discrepancy was way bigger than that?
So there have always been kind of two schools of thoughts. I mean, if the camera is recording, okay, I couldn't explain the second school of thought and the reasons why later, but the thing is they're not burning anything in their core, right? So that's what makes a star, is that you have nuclear energy, you keep on emitting things and gravity fights against you. Well, these guys, they're just born with whatever they have from collapsing, and they keep on cooling for forever. And they have clouds in the atmospheres, which stars don't really have. So they are actually, like, they have always been kind of the missing link for years between stars and planets. That's why some people put them as stars, some people put them as planets, but they resemble way more a planet than anything. It's just, I guess, also because they're rogue, most of them. They don't have a parent star, so you kind of have to put them like planets, stars for some people.
Okay, then I guess we'll stop taking questions for now, and you can bring up more later if you have them. So we'll take like a 10-minute intermission, and then we'll start